So, good. So we're now going to basically go back to the Yellow Submarine project. I think that's what I talked about in the last video. And basically, in this session today, was going to be a bit short. I'm gonna try to kind of catch up, recap where I left, because that's important. Um, Let me open up Chrome and let me go to the projects folder. So here we go, Yellow Submarine. Oh, 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 oh. So, Yellow Submarine. I think there was a GitHub repo for this, or uh, but again, just probably. I think it was Musty Thoughts. His blog. Musty Thoughts. Projects. The mouse doesn't. Here we go. Projects. Good. So there are a bunch of projects in here, and then this is the one. So here's the code and the research and the paper. Basically, if I remember this well, this was QAOA, but QAOA, but applied to but so it's MaxCAD QAOA. So we've been dealing with this in the past videos, and actually we did do one MaxCAD video, but this was on the discrete variable quantum computing, not the continuous variable quantum computing, and that was what kind of that was the biggest hurdle in this project for me. Let me see. So license requirements, Yellow Submarine. Example Max. Can I just open Atom here? I don't think. I don't know if that works. Let's see. Because basically the gates that are being used are of course different concepts, although the underlying concepts are the same, but it seems that it actually... No, I don't want Quirk. I want to open... Reopen project, Yellow Submarine. Yay, here we are. Let me close Quirk. Good, so... What have we got here? Finally we got it to run, if I remember well. And then basically there's the example file and the MaxCAD solver file. So this is the actual class. Okay. What was the train and evaluate? Says all the solutions classically build circuit. So here you're building the circuit, and here there was basically append. And here you're putting the parameterized gates. Interferometer. So basically, this was the adjacency matrix of the graph. Arbitrary interferometer matrix used for the circuit, which I don't know what is it, but it's something for the circuit. And then here, structure of the layers used in the variational part of the circuit. Yeah. So here you've got the S gates, the D gates, and the key gate, and the K gates. Squeeze gates, displacement gates, and Kerr gates. And then you're just basically running the simulation. So this is QANA. So there's really, I think, nothing to understand in here apart from what those gates do and how is this then a good mapping for that particular problem. I mean, it's the MaxCat problem, right? So if you want to know how this is approached from a continuous variable quantum computing perspective, then go check out the other videos that I have. Where's the best like, because last time so if I go to studio and I go to the playlist, other features, playlists, and I go to Yellow Submarine project review, 12 videos. So I went through all these, then I did QAOA, but this was the classic stuff, and then so then I was basically, these last two videos were on using CV quantum computing, and then I was going through that paper that was basically, I think, referenced in Miha's paper about how to encode a graph on a CVQC state. And I think that was quite lost in there. So, this mouse goes, it moves really awkwardly. So this is the paper. So maybe I should focus on that, because basically I'm assuming that's going to be then the theory behind. I mean, I think I went through that, yeah. The MaxCat problem, the circuit design, exactly. Solution encoding. Training, so that's kind of the classical part, right? How you're going to optimize your parameters, and then the results. And I think there's influence of non-Gaussian gates, loss function, displacement gate parameters, squeeze gate, cubic phase gate, conclusions, and then references. And there's an introduction to continuous variable quantum computing that I went through as well. You've got your Q modes, vacuum state, and there's Gaussian states and operators. And basically and then basically going through the different operators, the displacement operator, the squeezing operator. Yeah, so I remember position and momentum. These were the two kind of things being sort of measured or tracked, and so those gates were playing on those, so reducing uncertainty in either position or momentum. The displacement was basically increases the measured position and the measured momentum, so it literally displaces, because this was I think this is basically based on Xanadu's computer, so this is all photonic quantum computing. And then there are non-Gaussian state and operations. cubic phase operator, care operator. Proceed number operator with parameter k. Okay, then the different measurements. Photon counting. Yeah, I think that's a good starting point. And then here there had to be the reference to the other paper that I was going through. We'll probably have to find it. Give me a second. So give me a second, I had to pause for a second. Okay, what happened? Okay, so login again. Okay. So far I'm just flying over those topics. Quantum circuit as machine learning model. Okay. Yeah, okay, so we checked that all. Basically, acknowledgements, blah blah blah, organization. I kind of like the paper because it's pretty self-introductory, and then there's a bit of an introduction to the continuous era quantum computing, and so I think I should probably go through that a bit more carefully. Because then there's a bunch of experiments that I also wanted to basically go through. Check reproducibility. Main runner. Experiments. Okay, so this is the Submarine. Okay, yeah. Right, parameters investigating layers. Report. Current report 9 months ago. The main goal of this test is to investigate how the non-constant layers influence the output. The value of the cubic gate parameters changes during the training in opposition to the value of the Kerr gate parameters, which don't change at all. Even when cubic gates are used, it has no influence values of trace, at least not significantly. Cubic gates. Conclusion: the parameters of cubic gates are changing during the training. So good, back. Yeah, sorry, it's a bit of a distracting day. Morning. So good. So I think that's something that I'll probably do as a closing of this project. Is I will try to go and reproduce those experiments. ML approach. What was this one? So here you've got a bit of a different report, current report. This experiment, instead of training the circuit to solve a single graph, we took an approach more akin to machine learning. We're training a single network using several different graphs and checking if it generalizes well. This report is an updated version with a backend preparation of state fixed 10H changed to arc10H code. TensorFlow problems. The machine learning approach works as follows. post algorithm wasn't able to learn solving a Maxcap problem based on the input state. Okay. And then basically there's another one which is so Gaussian versus non-Gaussian. Report. So what do we get? What have we got here? We seek to determine if the presence of non-Gaussian gates is beneficial to solving the Maxcap problem. Weighted. Overall observations. Important notes. Presence of cubic phase gate doesn't yield any performance improvement. So Gaussian gates are sufficient to solve the Maxcap problem. Okay. Interesting. Embedding influence. Report. Description, observation, subscription 1. So the goal of the experiment is to determine what is the influence of using embedded graph in the optimization process. We have done simulations using weighted and unweighted graphs from previous experiments. In all cases, in the presence of the embedding, the final value of the cost function was either slightly worse or the same as without it. It seems that the presence of the embedding has no positive effect on the results of the algorithm and might have some detrimental effects. The circuit uses more gates, the algorithm might converge to higher value of the cost function, convergence might be slower. It will be interesting to try to reproduce some of those reports, even maybe these ones. So probably, I mean, that could be a nice thing to do. Try to reproduce that, because if I remember well, the version that I had was working. Basically, it was based on this. So if I run this, that was running. Oh, sorry. Example BI. Paste. And I think that was running, if I remember well. What is all this? Hyperparameters, eigenvalues. Graph was finalized. Okay, I'll let it run for a while, but I think that's basically what I wanted to do to close these. Kind of try to reproduce that. So, but it might be worth reading that paper again. from June this year. It's interesting. Related work, acknowledgements, the operation of quantum, creating quantum algorithms and variational circuits, algorithms and variation of quantum VQE, QAOA having been employed to graph problems like MaxCAD, use discrete variable quantum computing paradigm, and there has not been much work done to solve this with continuous variable quantum computing. Yeah, so benchmarking the variational optimization algorithm, we decided to follow this trend. We have based our work on the methods described in 1011 and developed them further to solve the MaxCAD problem on a simulator of a photonic quantum computer. 10 and 11 quantum neural networks. Oh yeah, I think these were the two papers that I was talking about. Yeah, that's the one with the fancy images. That's the one with the fancy images, and then 11 continuous variable quantum neural networks. Okay, so this kind of, okay, so this it actually run. Here you've got basically the displacement gates, Kerr gates, squeeze gates, total cost, loss function at the end. Here you have all the different steps. Cost, loss, regularization step, trace. Okay, so it's running, so it's good. Yeah, so I'll do one. What is this? Displacement. This is all based on these two papers. I'm trying to think about what's the strategy for the next steps in this direction. So because I probably should run through this again, and I think now that have a more solid background about QA, QAOA, VQE, the MaxCAD problem, then it might actually be easy to understand. So I think that's first step, is I'm going to go through this paper again, and maybe I'll start from the appendices as well, with the introduction, and so this is probably going to be next step, and then the other one, and then step by step I'll try to basically reproduce the research that is in here. I'm not sure if I'm going to do all of them, but I'm definitely going to do, because I think check reproducibility probably is not needed, but I don't know, we'll see. The embedding influence, investigating layers, those are interesting ones. So I'll just go and see if I can kind of basically make the same observations that they make in here. Code-wise is, I think, simple enough that it's manageable. I just want to make sure I understand everything, and then I basically reproduce the observations, and I think that's going to be helpful for Michał and for the team behind this. Yep. Okay, but I think that was a good recap. I probably should bookmark some of those things. Yeah. Perfect.